Welcome to Review Lecture 5.3, Resistors and Circuits. Upon completion of this, you should be able to calculate the equivalent resistance of resistors in series and also parallel and also combination, and compare the equivalent capacitance formula with the equivalent resistances formula. Three lamps are connected in series, one after another, like a daisy chain with a battery. They form a series circuit. In other words, there's only one path for the charge to flow, and the charge flows through each in turn. When the switch is closed, the current exists almost immediately in all three lamps. The on signal travels at the speed of light in the wire. The electrons move, of course, we know they move a lot more slowly. The current does not pile up in any lamp, but flows through each lamp. The electrons in all parts of the circuit begin to move at once as the on signal reaches them nearly simultaneously. Eventually, the electrons will move all the way around the circuit. Now, a break anywhere in the path opens the circuit and the flow of electrons immediately ceases. Burning out one of the lamp filaments or simply opening the switch or unscrewing the balls breaks the circuit. It's like an old-fashioned Christmas tree light string. Remember those? Yeah, if any of the lamps blew, you had the devil of time trying to figure out which one it was because they'd all turn off and you had to sit there and replace them one by one. My dad and I would get at each end. He'd start at one end and I'd start at the other and we replace them and then meet in the middle. We made it go faster. Now, there is only one path for the flow of charge or current. All the current flows through each part of the circuit. Current I is the same everywhere in the series circuit. Ohm's law still applies. V equals IR. The current in the circuit equals the voltage supplied by the source divided by the equivalent resistance of the circuit. Potential drop across each resistance in the circuit equals the current times the resistance, that resistance. So Vj equals IRJ. Now we're using J as an index here because otherwise we get confused with I, which is the current. So now we're going to have this circuit. There's three resistors connected in a series, and we want to find the one equivalent resistance that we could use to replace all of these three. Potential difference E is maintained across A and B by the ideal battery. The same current flows, because there's no place else for it to go, through each resistance and through the entire circuit. So this I here is the same as that I, and this I equals that I equals that I equals that I. Okay, so we apply the loop rule to both circuits. We're going to go clockwise. We're going from the negative to positive plate, so that's positive E. We're going with the current that's down the waterfall, so that's minus IR1, minus IR2, minus IR3, and we're back to our starting point, so that equals 0. We solve this for the current. It'll be the EMF of the battery divided by the sum of the resistances. We check the units. It is volts divided by ohms, that's amps. And then we can look at this one down here. We have E minus IR equivalent equals 0, or I equals EMF over R equivalent. And if we equate these two, take out the like terms like the I and the E's, we end up with R equivalent as R1 plus R2 plus R3, or R equivalent is the sum of all the individual resistances. So resistors sum in series. We've summed over index J because otherwise it would get too confused with current I. So here's our equivalent equations. Resistors add in series. The equivalent resistance of resistors connected in series is the sum of all the resistances. The equivalent resistance of a group of series resistors is greater than the largest individual resistance. Makes a good way of checking this. The potential drop across any resistor is the current, which is a common current, times the resistance of that resistor. So Vj equals IRJ. The total potential drop across resistors is the sum of the individual potential drops across each resistor because potential drops add in series. So V equals the sum of the Vj's, which we can pull the common current outside, so I times the sum of all the RJ's. As you add resistors, the overall resistance increases and the current from the source decreases. For n equal resistances in series, the equivalent resistance is just N times RJ, where RJ is the resistance of one resistor. Now, parallel circuits have multiple paths for the current to flow. This is a parallel circuit having three lamps. Each electric device, each lamp has its own path from one terminal of the battery to the other. There are separate pathways for the current, one through each lamp. In contrast to the series circuit, the parallel circuit is completed whether all two or only one lamp is lit. So if you unscrew this one, only that one goes out. If you unscrew this one, only this one goes out. If you unscrew both of them, this one still stays lit. A break in any individual path does not interrupt the flow of charge in the other paths, which is the advantage of a parallel circuit. So each device connects the same 2 points A and B of the circuit. So therefore, VAB is the same for all of them. This voltage is the same as that voltage, the same as this voltage. The total current divides among the parallel branches. So we have the amount of each current in each branch is inversely proportional to the resistance of the branch. The total current is the sum of the currents in the branches. I equals I1 plus I2 plus I3. As you increase parallel branches, The overall resistance decreases because there's more paths for the current to flow, and the total current through the battery increases. So resistors in parallel, we want to make this circuit look like that one. So we want to find the equivalent resistance that can replace these three parallel resistors. So we're going to first write the current in each actual resistance. I1 will equal V over R1, I2 equals V over R2, and I3 equals V over R3. V is the common potential difference between points A and B. It's also equal to the potential rise across the battery. We can apply the junction rule at point A. If we do that, we find that I, which is this current through the battery, equals I1 plus I2 plus I3. The other way you can look at that is down here at point B. You can see that I here equals I1 plus I2 plus I3. Okay, so we can plug this into that. So then we wind up with I equals V times the quantity, 1 over R1 plus 1 over R2 plus 1 over R3. If we replace the parallel combination with the equivalent resistance R equivalent, we even have I equals V over R equivalent. And thus substituting the value of I from the previous equation, we get 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. So resistors add as 1 over. 1 over R equivalent equals the sum of 1 over Rj, where Rj are the individual resistances. They act like capacitors in series. So pair resistance, we can do products over sum. So R equivalent is R1, R2 over the quantity R1 plus R2. So resistors add as inverses in parallel. The equivalent resistance of a group of parallel resistors is less than the smallest individual resistance of the group. The potential drops across all the resistors is the same and equals the voltage supplied V at the source. The current from the source equals the sum of the current in the branches, so that just sum them up. The current in each branch divides according to the inverse of the resistance of the branch, so Ij equals V over Rj. As you add branches, the overall resistance drops and the current from the source increases. For n equal resistances, that is, each one's equal to Rj, the equivalent resistance is just Rj over n. Comparison here. Capacitors. Capacitors add up in series, add up as 1 over. In parallel, they add. So memory aid, capacitors add in parallel. Resistors add in series. In parallel, they go as 1 over. So again, resistors add in series. Notice that there's opposites here. We're going to find out batteries and inductances work a lot like resistors. So when you have combination circuits, so it's just like we did with combination capacitors. Remember that? We identify the parallel bits and the series bits. We analyze the individual bits using the rules for parallel and series. And then we find an overall combined resistance, and we'll do some examples. Here's one of the examples. We're going to turn this circuit, which has 2 parallel resistors and then a series bit here, into this one. So what you do is identify bits that are purely parallel or purely series. We analyze them using the rules for parallel and series, and then we combine them. In this figure, R1 and R2 are in parallel, and there's only 2 of them, so we do product over sum. R12 is R1, R2 divided by R1 plus R2, so that's this equivalent. This replace that. Now, R12 is in series with R3, so then they just add. So R equivalent is R12 plus R3. We can substitute. R equivalent is R1, R2 divided by R1 plus R2, all plus R3. And that's what we've got here. So here's some more examples. We have a bunch of 8 ohm resistors. Okay, one's in series with 2 that are in parallel. So we look at the 2 8 ohm resistors that are in parallel, and we can do product over sum. And we do that if they're equal. Here's another tip. If they're equal, this becomes R1, R1 divided by R1 plus R1, or 1/2 R1. So the equivalent resistance for a pair of equal resistance in parallel is half the value of either one. The equivalent resistance for this pair then is 8 over 2, which is 4. The equivalent resistance, of course, is less because the current has twice the path widths, so it has half the resistance. This 4 ohm resistance is now in series with the 8 ohm resistor, this one over here, and so that adds. So it's 8 plus 4 is 12 ohms, so that'd be the equivalent resistance of this group. Okay, now we're going to do this group. We have a 60-volt source. We have 2 10 ohm resistors in series with each other. That group is in parallel with this group. This group is a 16 ohm resistor in series with 2 8 ohm resistors in parallel. First thing we do is to take these 2 8 ohm resistors and replace them with an equivalent one. So the first 2 8 ohm resistors are equal and they're in parallel. So the equivalent resistance is half of one of them, or 4 ohms. That's this right here. The second picture says that these two are in series with each other. So it's 16 ohms plus 4 ohm equals 20. These two are also in series with each other. So 10 plus 10 equals 20. Then we wind up with this picture here. These two are equivalent and they're in parallel with each other. That means the equivalent resistance is going to be 1/2 of 20, which is 10. This is the very last picture here. That means we have a 10 ohm resistor that's equivalent to all of these that is connected with a 60-volt source. So that means this equivalent here has a single 10 ohm resistance, which could be used to replace all of the other resistors in the original circuit and still draw the same current from the battery as the original circuit. So now we have a multi-loop circuit containing one ideal battery and 4 resistances, R1, R2, R3, and R4, with the following values. E is the 12 volts, that's the battery. R1 equals 20 ohms, R2 equals 20 ohms, R3 equals 30 ohms, and R4 equals 8 ohms. What is the current I1 through the battery? What is the current I2 through R2? What is the current I3 through R3? Okay, the physics of this is resistances in series and parallel, and of course we can always use Ohm's law for this. We write down knowns and unknowns. R2 equals 20 ohms, R3 equals 30 ohms, R4 is 8 ohms, EMF is 12 volts, R1 is 20 ohms, I1 is what, I2 is what, I3 is what. We're going to identify bits of the circuit. R3 and R2 are in parallel with each other. Now, in case you can't see that, you can lengthen this wire and move this resistor over here. Okay, now you cannot move anything past a node or a junction, but it's okay to lengthen this and move this resistor over here. If you do that, then you can very clearly see that R3 and R2 are in parallel with each other. So, and there's only 2 of them, so we can do product over sum. R2 divided by R3 plus R2. So 20 times 30 divided by 20 plus 30, 12 ohms. So this is now 12 ohms. That's the equivalent to this. And this makes sense because this is less than 20. It's less than the smaller one. Okay, pretty much the same thing. Now we have the equivalent resistance for the series circuit. We're going to turn this, okay, into something that just has a battery and 1 resistor, which I didn't show here. So we're going to find the equivalent resistance for this, and that would be R1, 2, 3, 4. He has to equal R23 plus R1 plus R4. So R23, that's a parallel bit we just solved for, plus R1 plus R4. So R1, 2, 3, 4 is 12 plus 20 plus 8 ohms, or 40 ohms. This is a simple battery series resistor circuit, and Ohm's law says E equals I1 times R1, 2, 3, 4. We can solve for I1. I1 is the current from the battery. It's also the current through R4 and the current through R1. So I1 is E over R1, 2, 3, 4, 12 volts divided by 40 ohms, or 0.30 amps. That's I4. That's the current from the battery. Now this current splits. We're going to go back to the original circuit. This current splits at point B here in the parallel part between R2 and R3. So V2, these are parallel. So V2 equals V3, and that equals V23, and that equals I1 times R23. Okay, so that's 0.30 amps times 12 ohms, or 3.6 volts. That potential drop here, right here, has to equal this one, and also has to equal this one, because they're in parallel. So V2 equals I2 R2 has to equal I3 R3, and that has to equal 3.6 volts. And we can use this to get I2. I2 equals V2 over R2, which equals 3.6 volts divided by 20 ohms, which equals 0.18 amps. I3 is V3 over R3, or 3.6 volts divided by 30 ohms, which is 0.12 amps. And you can see the larger resistance has the smaller current. And if you add the 2 currents up, you wind up with a current I1. So that checks out okay. You should always do checks like this. Okay, now how do batteries work in series and parallel? When you connect batteries in series, they look like a daisy chain. The positive terminal of cell 1 is connected to the negative terminal of cell 2. Cell 2's positive terminal is then connected to the negative terminal of cell 3, and so on. It's like a 3D cell flashlight. All the batteries have to be in the same direction, or else it doesn't work. Now, for n similar cells with internal resistance Rj, EMF Vj, and potential Vj, and current Ij, okay, the internal resistances add. So R equals R1 plus R2 plus R3, or if they're all the same, that equals the number of batteries times the internal resistance of one of them. Similarly, the EMFs add, so E equals E1 plus E2 plus E3, and if they're all the same, it'll be the number of batteries times E of one of them. Similarly, V equals V1 plus V2 plus V3. If they're all the same, it'll be the number of batteries times V of one of them. These equations have the same form as those for resistors in series and can be extended to any number of cells. Now, the other main way is to connect batteries in parallel. This is an equal potential surface called a bus. The positive terminals of all the cells are connected to a common wire or common bus. The negative terminals of all the cells are then connected to another common wire or negative bus. And we would put the circuit across here, obviously. For n similar cells with internal resistance Rj, EMF Ej, potential Vj, and current Ij, currents add in parallel. So I equals I1 plus I2 plus I3, which will equal N times I self, they're all the same. Currents go as 1 over in parallel. So 1 over R equivalent is going to be 1 over R1 plus 1 over R2 plus 1 over R3. Or if they're all the same, R equivalent is going to be R cell divided by N. EMFs are all the same. So E equals E1 equals E2 equals E3 equals E cell. V's are all the same. So V equals V1 equals V2 equals V3 equals V cell. Now the warning about these is that they aren't all the same. It'll be the weakest one. So in other words, the lowest E and the lowest V. Now these equations have the same form as for those for resistors in parallel and can be extended to any number of cells. The electric eel actually is a really fantastic animal. They can generate current with biological EMF cells called electroplaques. In the South American eel, they are arranged in 140 rows, each row stretching horizontally along the body and each containing 5,000 of these electroplaques. Each electroplaque has an EMF of 0.15 volts and an internal resistance of 0.25 ohms. The water surrounding the eel completes the circuit between the two ends of the electroplaque array, one at the head of the animal and the other near the tail. If the surrounding water has a resistance of 800 ohms, how much current can the eel produce in the water? How much current I rho travels through each row, and would it hurt the eel? How much voltage does the eel generate? Now here's its circuitry. These are 5,000 little individual cells called electroplaques in each row, arranged in series with each other. These rows are 140 rows arranged in parallel with each other. The physics of this is real batteries in series and parallel, and of course resistances in series and parallel in Ohm's law. So you write down your knowns and unknowns. We know the number of rows, it's 140 rows. The number of cells, it's 5,000 cells per row. The EMF of each cell is 0.15 volts. The internal resistance of each cell is 0.25 ohms. The resistance of the water is 800 ohms. We need to know the current. We need to know current in each row. We also want to know how much potential does he produce. For N batteries of EMF EJ and internal resistance RJ in series, ES equals N EJ, RS equals N RJ. For N batteries of EMF EJ and internal resistance RJ in parallel, E parallel equals EJ and R parallel equals RJ over N. Now, the approach to this is all the small batteries are the same. We're going to break it up into series bits and parallel bits. We're going to combine the series EMFs in the row into their equivalent row EMFs. So we're going to put all these together. We're going to combine the internal resistances into equivalent row resistance. Then we're going to combine these parallel row EMFs into equivalent overall EMF. And then we're going to combine the row resistances into equivalent overall resistance, and then use Ohm's law. Okay, so for series parts, the equivalent is just the sum of all the individual EJs. R equivalent, similarly, is all the sum of all the RJs. For the parallel goes 1 over R equivalent equals the sum of 1 over RJ. And I will then be E over big R plus little r. So that is just the equivalent circuit overall. Now, for the algebraic solution, E rho is just N cells times E cells, or R rho is just N cells times R cell. But 1 over R equivalent is N rho times 1 over R rho. So R equivalent combining these is R rho over N rho. R equivalent is the ratio N cells over N rho times R cell. I is E over big R plus little r, which equals E rho over RW plus R equivalent. So now we can start putting numbers in. E rho is just the number of cells times the EMF of one cell. It's 5,000 times 0.15 volt. So it's a 750 volt. That's pretty respectable. This is the EMF the eel generates. R equivalent is just the number of cells divided by number of rows times R cell. So that is 5,000 divided by 140 times 0.25 ohms. Equivalent resistance of the whole eel is 8.93 ohms. Okay, then we need the total current and voltage generated. So I is just E rho over the combination of RW plus R equivalent. So it's 750 volts divided by 800 ohms plus 8.93 ohms, or the current is a very respectable 0.93 amps, which is almost 1 amp. That's pretty good. Now this is more than enough to stun or kill a fish, which fish are their prey, or an unwary human who tries to catch the eel. So V equals just E rho minus IR equivalent, or 750 volts minus 0.93 amps times 8.93 ohms. So that's the voltage that he generates. That's 742 volts. Now this is the output voltage and is potentially fatal for anyone who messes with the eel. Now they had an electric eel in the Cincinnati Zoo in the aquarium, and everybody loved to see the eel when they fed him, because they didn't throw live prey into him, they just gave him dead fish. But they had a bank of light bulbs in with the eel. And whenever they feed him, he would light up those light bulbs because he didn't realize the fish were dead and he was trying to shock and kill his prey. And this is what he was producing. It was pretty impressive. And of course, they made absolutely sure nobody could stick their fingers in the tank. Yeah, that would have hurt like crazy. Okay, so the current per row is I rho equals I over N rho. The numerical solution then becomes, the current then is 0.93 amps divided by 140 rows, or 6.6 milliamps. This extremely weak current is way too small to harm the eel, and it's very easy for the eel to generate. In other words, it's basically a marvel in engineering. But it's amazing how he's managed to get this circuitry. That's fantastic. Okay, now parallel circuits and overloading. Now, the problem with parallel circuits is that the currents add. Get the current from this, the current from that, the current from that adds up to a total current of 20 amps in this. And this can cause problems. So to prevent overloading of circuits and fires in the wall from overheated wiring, fuses or circuit breakers are connected in series along the supply line. So this means in this case, the entire current from the circuit passes through the fuse. All fuses are rated by the max amount of current that they will pass without blowing. If a fuse is rated at 20 amps, it will pass 20 amperes, or anything less than that. A current above the rating will melt the fuse ribbon, which blows it out and breaks the circuit. Fuses which blow need to be physically replaced to restore the power to the affected circuit. Never replace a fuse with one of a greater rating, or the circuit will be protecting the fuse rather than the fuse protecting the circuit, and then you probably will have a wall fire. You don't want a fire in your walls. That makes your day really bad. If fuses blow repeatedly, reduce the load on the circuit. If that does not help, have a qualified electrician check the wiring. Before a blown fuse is replaced, the cause of the overloading should be determined and remedied. Insulation that separates the wires in a circuit can wear away or degrade over time, and this can allow the wires to touch. This effectively shortens the path of the circuit. It's called a short circuit. A short circuit will draw an abnormally large current that becomes dangerous because it bypasses the normal circuit resistance. This current causes the wires to overheat, possibly causing a fire on the walls of your house. That kind of fire is extremely difficult to detect, and it can burn down your house. Now, circuits can also be protected by circuit breakers, which are automatic switches that use magnets or bimetallic strips to open the switch when excessive current is sensed. Utility companies use circuit breakers to protect their lines all the way back to the generators. Circuit breakers are used in modern buildings because they don't have to be replaced each time the circuit is open, and there isn't the temptation to replace the circuit breaker with one of a larger fuse. You just reset the breaker, usually by throwing the switch or pushing the reset button. It's still very important to correct the problem that caused the overload. Now, some ideas for electrical safety. Stay dry. Dry skin has a higher resistivity than wet skin. Don't use appliances around water. Stay off wet ground when using electricity. Wet ground can complete a circuit and allow you to get a shock. Inspect cords regularly. Do not use any which are frayed or damaged. Never pull the plug by pulling the wire. Grasp the plug, not the wire. Do not place cords where they can be damaged or tripped on. Keep kids and pets away. Never alter a plug. Do not break off the round grounding prong or file down the wide prong. If an appliance gives you a shock or sparks or smells like burning insulation, don't use it. It's not worth your life. Do not try to convert a polarized plug to a non-polarized one by filing or cutting down the larger prong. Doing so may energize the appliance case and shock you. Install GFCI outlets in wet areas of your house, such as bathrooms or kitchens and laundry rooms. GFCI stand for ground fault circuit interrupter. They detect and cut off small leakage currents before they can injure or kill you. There are also GFCI extension cords for use outdoors. Never replace a blown fuse with one of larger rating. Unless you know what you're doing, have a qualified electrician do any rewiring in your house. If you blow fuses or pop breakers frequently, or there's a smell of burning insulation in your house, stop using the affected outlets or circuit. Have it checked out by a qualified electrician before you use it again. It's not worth your life. Be sure to be careful when you're using extension cords and power strips. Do not exceed the cords or strips rating. Don't use extension cords or strips that are indoors, used only outside. Don't place cords or strips where they can be damaged. An electric meter measures the amount of energy used in kilowatt hours. Never fool around with an electric meter. Doing so is illegal and extremely dangerous. Keep the meter free of ice and snow in the winter and wasps and birds' nests in the summer. Be careful when using wasp killer spray. Some can conduct electricity. Never touch the downed power line or anything that might be touching the wire. Treat all power lines as live and lethal. Stay at least 25 feet away. The ground can carry currents for amazing distances. If you're in a car, do not try to leave the car. You're completely safe inside the car, and yes, you can safely touch the metal inside the car. When filling up the pump, stay outside the car. Place any gas can on the ground before filling it up. Charge can build up on the car, the gas can, and even on your clothing and even on you. You want to keep everything at the ground potential like the gas pump, so you do not get a spark or fire and explosion. During thunderstorms, stay away from plumbing. Stay off the phone except for wireless ones. Your cell phone is okay as long as it's not plugged into the charger. Do not use or touch electrical appliances. Lightning can travel more than 20 miles. That's the origin of the bolt out of the blue saying, and do very strange things. On top of that, the lightning that travels the furthest is typically the stuff off the positive tops of the cloud tops. That's called positive lightning, and that can pack a wallop that's more than 10 times what normal lightning is. Yeah, you don't want to get across that. Never take refuge from a thunderstorm by standing under a tree. And if you're on the golf course or on the water, get into a building or your car fast. The safest place is inside a metal box like a hardtop car or metal building. If your hair starts to stand on end, place your feet together with your ankles touching each other. Squat down. Do not lay down on the ground. Place your hands over your head and stay as low to the ground as possible while touching the ground as little as possible. So in other words, minimize the area in contact with the ground. You don't want a ground current going through you. During a thunderstorm, the safest place is inside a metal box like a hardtop car or metal building. And no, it's not because of the rubber tires. Note the arc on the front tire in the picture. Modern tires are made to be conductors. They have steel belt radials and they have carbon in the rubber. Like charges repel, they try to get as far away from each other as possible. That is on the outside of a conductor. Remember, charge is free to move in the conductor, so the charges move to the outside and flow around the outside. No charges on the inside, so the man inside the car is safe. Another way to look at this is that the body of a conductor is an equal potential, all at the same potential. Since it's potential difference that kills, and equal potential by definition has no potential difference, the man inside the car is safe. Judging from the arc here, that's about 6 million volts. He's at 6 million volts, the car is at 6 million volts. As long as he stays inside the car, he's okay. Now, if he gets out of the car, that's not what he wants to do. The three resistors, 10 ohms, 20 ohms, and 30 ohms, are connected in series. An EMF of 100 volts is applied. Which resistance has the highest voltage drop, and which resistance has the largest current? I can answer the second part of this question first. They're in series. They're all going to have the same current because there's only one path for the current to flow. And the one that will have the highest voltage drop, V equals IR. So it'll be the one with the greatest resistance. So answer that. First part of the question is 30 ohms. The second part of the question is all the same. Three resistors, 10 ohm, 20 ohms, and 30 ohms, are connected in parallel. An EMF of 100 volts is applied. Which resistance has the highest voltage drop? This is a trick question. They're in parallel. So the voltage drop is going to be the same across all of them. Which resistance has the highest current? Current is inversely proportional to resistance. So the smallest resistance will have the highest current. So the answer to the first part of this, it's number 4, is all the same as in parallel. The answer to the second part is 10 ohms, I equals V over R. Three identical resistors are connected in series and powered by a 9-volt battery. What is the voltage across one resistor? Well, the resistors are all identical. So we'll split this 3 ways. So 3 volts plus 3 volts plus 3 volts equals 9 volts. 3 volts. So since the resistors are all equal, the voltage should drop evenly across the 3 resistors, 1/3 of 9 volts across each one. So we get a 3-volt drop across each. A 4 ohm and a 2 ohm resistors are connected in series and powered by a 12-volt battery. What is the voltage drop across the 4 ohm resistor? It's going to be 8 volts. Resistors add in series and the current is the same through the circuit. So R equivalent is 4 plus 2, or 6 ohms. I will be V over R equivalent, which is 12 volts divided by 6 ohms, or 2 amps. Voltage across the 4 ohm resistance is going to be the current times the 4 ohm resistance. So 2 amps times 4 ohms are 8 volts. We can always check this. Calculate the voltage across the 2 ohm resistor. That's 2 amps times 2 volts. That equals 4 volts. By Kirchhoff's loop rule, the voltage rise in the source has to equal the voltage drop in the resistors. So the EMF of the battery has to equal the 8 volts plus 4 volts lost in the resistors. And it does. 12 volts equals 12 volts. You should always check things like this. A 2 ohm and a 5 ohm resistor are connected in parallel, powered by a 10-volt source. What is the current through the 5 ohm resistor? This one's easy because they're in parallel. The voltage drop across these is going to be equal to the voltage rise across the battery. It's just going to be I equals V over R, or 10 volts divided by 5 ohms, or 2 amps. When you add resistors to a circuit, you increase the equivalent resistance of the circuit. This is a trick question. Only if the resistance you add is in series with the rest of the circuit. Resistors add in series, not in parallel. If you put a parallel one in there, it's going to lower the overall resistance. The circuit of parallel resistors is connected across an ideal battery of fixed voltage. As more resistors are added to the parallel circuit, what happens to the total current in the circuit? Ignore P and Q. And what happens to the current through each resistor? Well, answer to the first question is that the current will increase. So the ideal battery will supply a constant voltage. As you add parallel paths, the current from the battery rises because you lower the overall resistance of the circuit. What happens to the current through each resistor? The current through each resistor stays the same because V is constant. The light bulbs in the circuit are identical with the same resistance, R. Which circuit produces more light? Power is proportional to brightness. Assume the resistance of the bulbs does not vary with temperature. Well, it's going to be circuit B. Okay, in B, the bulbs are in parallel. That lowers the overall resistance of the circuit. So this is going to draw more current, which will lead to higher light. Also in circuit A, each bulb shares the potential difference across the battery. and P is proportional to V squared, so each bulb is going to be much dimmer than it is in point B. So A is going to be a lot dimmer than B. What happens to the voltage across resistor R1 when the switch is closed? Assume the battery supplies a constant V. So this is the switch S. Okay, it's going to increase. Now we look at R equivalent. R equivalent is going to be the R, the parallel part, plus R1. When you close the switch, you increase the number of paths in the parallel part. That decreases this RP. Since R equivalent is RP plus R1, this also decreases R equivalent. Since I equals V over R equivalent, the current from the battery and that through R1 will also increase. Since RP and R1 are in series, all the current flows through R1. So V1 equals R1, so then V1 will increase. What happens to the voltage across resistor R4 when the switch is closed? Assume the battery supplies a constant voltage. It's going to decrease. R equivalent is R, the parallel part, plus R1. When you close the switch, you increase the number of paths in the parallel part, which decreases the resistance of RP. Because R equivalent is RP plus R1, when RP decreases, so does R equivalent. I equals V over R equivalent, so the current from the battery and that through R1 increase, since RP and R1 are in series and all the current flows through R1. V1 equals I R1, so V1 increases. Since V is constant and V equals V1 plus VP, which also equals V1 plus V4, okay, because the voltage across parallel parts is the same, so VP equals V4, so V4 also decreases. Two identical incandescent bulbs are connected as shown to a constant voltage source. When the switch is closed, bulb A will blank and bulb B will blank. Well, bulb B is going to go out, and all the current's going to flow around this shunt here. A shunt is otherwise known as a short circuit. And that will allow this potential here to be completely across A instead of being split. So bulb A is going to get brighter and bulb B goes out. Okay, by closing the switch, you short out bulb B, provides a low resistance path around the bulb. Almost all the current flows through the switch and very low flows through the bulb, which then goes out. This lowers the equivalent resistance to that of bulb A alone. So the current increases in the circuit, and that increases the power and brightness of bulb A. Thank you.